to Buket Benek Gursoy, who is a computational scientist at the Irish Centre for High-End Computing in University Galway. Her presentation is entitled Performance Engineering for Scalable Earth Observation Data Analytics. I hope you enjoyed the session, and I'll hand the floor over to you, Buket.
Thank you, Sandra. Hello, everyone. This is Buket. Thank you very much, Sita, Sandra, and Marion for the invitation. It is great to be presenting here today. I am a computational scientist in ICHEC, which stands for Irish Centre for High-End Computing. My background is on applied maths. I have a PhD from Maynooth University, and I am involved in the performance engineering team, as well as training and education program in ICHEC since 2012. Okay, first a little bit about ICHEC. ICHEC is Ireland's National Centre for High Performance Computing, or HPC. It was established in the University of Galway in 2005 and funded by Department of Further and Higher Education, Research, Innovation and Science. We currently have offices in both Galway and Dublin. And we are a team of around 50 people coming from diverse backgrounds. Our main goal is to provide computing resources, infrastructure services, and expertise in HPC to all Irish higher education and research institutions. Furthermore, we have activities in additional areas of research around HPC, including AI, data analytics, quantum computing, environmental science, as well as engaging with a large number of public sector, industry, and involving in international collaborations. So as we will talk about HPC and AI workflows today, let me start with a simple motivation. Many AI projects begin on a personal laptop or a workstation, which is great for prototyping, working with small data sets, or for short training runs. But as your data sets grow, or your models become more complex, you will hit the limits on GPU performance and storage. And that is where HPC comes in. HPC, or high performance computing, refers to powerful computing systems that combine many processors to solve large complex problems much faster than a single computer. And these systems are called supercomputers. Since 2005, ICHEC hosted Ireland's national supercomputers, and the most recent system, named K, was decommissioned in June 2024. Since then, we have been using Meluxina supercomputer based in Luxembourg as an interim service until the launch of the next system, Caspir, which is expected to go online in 2027. Meluxina is part of the EuroHPC network. EuroHPC is a joint initiative across European countries that provides shared access to powerful computing systems across Europe. Meluxina was launched in 2021 and ranked 36th worldwide for computing performance of 10.52 petaflops. So it can perform 10 million billion operations per second, so a number that looks like this. And it was the greenest HPC in Europe at the time. And the system is water cooled, and it relies on AMD processors and NVIDIA A100 GPUs. So you can see in this picture what it looks like. So each of these large cabinets is filled with computing nodes. A node is like a single powerful computer containing a mix of multi-core CPUs and multi-GPUs and memory. And many nodes are connected through a high-speed network and linked to a large shared storage systems which hold the data. And the system provides the required software environment with scientific and AI tools ready to use. Recently, Ireland has been awarded as an AI factory antenna, and this was led by ICHEC in partnership with CDAR at UCD. Antenna in Ireland will give access to AI factories across Europe, and these are the Euro HPC AI-focused supercomputers. So very soon we will be supporting many AI workflows of our users, and that's why we are investing so much of our time in understanding and improving our performance engineering skills for modern AI workflows to run efficiently on these systems. So what is performance engineering then? It is a well-defined, structured process to identify the relevant performance bottlenecks and then derive appropriate code changes or other measures to improve the resource efficiency of programs. And the term has been used in HPC for any activity to improve time to solution for a given HPC application. But HPC applications are now moving from being traditional standalone applications towards complex and multi-stage workflows, combining HPC, AI, and quantum computing. They typically involve key stages, processing, using data analytics to prepare input data, to accelerate simulation setup. Simulation or modeling is where HPC plays a central role, and post-processing involves analyzing the results, visualizing outputs, and refining parameters. So as these workflows become more complex, the underlying computing architectures are also evolving towards more heterogeneous and integrated architectures. Modern systems often now combine CPUs and GPUs with specialized AI accelerators. We also increasingly see hybrid infrastructures that combine cloud resources with HPC systems. So this evolution brings powerful new capabilities, but requires also a shift from traditional code-level performance engineering to workflow orchestration to coordinate these multi-stage tasks, and architecture-aware optimization to adapt these workflows to a growing variety of compute architectures. So as a performance engineering team, we also have been adapting ourselves to this transition, and SHODA, Scalable Earth Observation Data Analytics, was one of the projects as part of Euro HPC, Euro CC program as a prototype to better understand data-centric Earth observation and machine learning workflows, and to help prepare ICHEC for Caspir. So in the Earth observation domain, key performance engineering topics begin with data pipeline, where efficient data access, storage, and pre-processing are critical, especially when working with large satellite data sets, and for efficient data flow across pipeline stages. Next is training to handle large-scale models with large data sets, we need scalable training strategies such as parallelism, batching, distributed computing across multiple GPUs or nodes. And then model efficiency is important as the model design and hyperparameter optimization directly impact performance. After that, inference. Once the model is trained, we want fast and efficient deployment. And finally, performance is not just about speed, but also energy efficiency. We need to aim to minimize resource usage and reduce the carbon footprint through energy-aware optimization. Now I am going to describe a use case within the SHODA project. But for this project, we were only concerned with the cost of training. So this is only the second item here. So in other words, the training time. So when we started the project, we were looking for a toy example to experiment. And this work was suggested to us by our domain scientist team in ICHEC. So it is it's based on FlatNet dataset. FlatNet is a challenge by Earth Vision 21 workshop for collaboration between computer vision specialists and Earth observation communities. I am sure you're already familiar with it. So this was specifically designed for post-flood scene understanding and flood management. So it includes low altitude, high resolution post-disaster images. And the images are labeled pixel-wise using specific color codes for semantic segmentation tasks. And each pixel belongs to one of the 10 classes, which are background, flooded or non-flooded building or road, water, tree, vehicle, pool, and grass. And this is the link here to the FlatNet paper by researchers from University of Maryland and Texas. So the data set is publicly available on Google Drive. So this is the last link here. And these are high-resolution aerial images captured by remote controlled drones after Hurricane Harvey in Texas on August 2017. And it contains around 2,300 high-resolution images in total, like around 13 gigabytes in memory. And the dataset is divided already into train, validation, and test sets. And each folder includes two subfolders, one for images and one for masks. Okay. So the implementation follows the classic AI workflow steps. Step one involves procedures for processing the images and their labels to fit for training model by resizing and normalizing. Step two involves choosing a model for the dataset as well as deciding the loss function, optimizer, and building the main training loop. So it uses DeepLab V3 Plus architecture from the segmentation models PyTorch library. But in the paper, they also test with some other model architectures as well, like UNet or PSPNet. And a standard loss function for multi-class classification is used, cross-entropy loss. And as an optimizer, Adam W was selected. So after training and validation, the best performing model was saved and evaluated using metrics such as pixel accuracy and intersection over union. So so the output is a predicted segmentation mask of the image. And the first column here corresponds to the images to be segmented, and the second to their ground truth segmentation masks, and the third one is the masks predicted by the code. And as seen in the last column, the model identifies mostly the roads, buildings, green areas for the sample, and inference gave pixel accuracy for this use case around 80%. So we basically reproduced their work in the paper to understand behind the scenes of optimization steps and the required tool chain. And this was an internship project under Shoda and producing early results on the ICHEC's case supercomputer and then running on GPUs on Meluxina. So the first approach, generally in performance engineering, is before trying to optimize a workflow, first to understand where the time is being spent. And this is called profiling. And profiling helps us to get a rough idea of the total runtime, identify which functions take the most time, and understand how different functions call each other. And for this purpose, the original code was locally run on a laptop on a Jupyter notebook, just for a few epochs, roughly, and profiled using a Python C profile to have some idea. And so we used then a cache grind tool to visualize the C profile output. So the functions statistics can be seen on the left as the top-down view. And then the call graph is generated on the right from the trace information gathered by C profile. And each node here is a function. It shows the inclusive percentage of time spent in that node and its children. And we can see from this graph that is expected that most of the time spent on training, 75%, which 44% is on backward operation, 30% is spent on forward, and 60% is on optimizer. Then we run the model on a single GPU, and it immediately reduced the runtime from like over 1 hour on the CPUs on Meluxina to 25 minutes on single GPU. So the idea on GPU offloading is that the model resides on the GPU, assuming that the model fits on GPU memory, and it receives input batches from the data loader, performs forward pass to compute the loss, followed by a backward pass to calculate the gradients, which then optimizer uses to update the model parameters. And in PyTorch, data loader handles this. It is responsible for loading data from disk and preparing batches for the training. And num-worker parameter here controls how many processes are used in parallel to load and process the data. So we consider it as our one of our hyperparameters. So we experiment with different values of these hyperparameters, type of model, optimizer, number of workers, batch size, and learning rate. And we observed this configuration to be the best setup, as it resulted in the fastest training time. Okay, so we used NVIDIA Insight System Profiler tool on the GPU because Meluxina has the NVIDIA GPUs and it has all the ecosystem for profiling and performance analysis tools. So we use the Insight System tool. And this is just a quick command line output. The first screenshot shows the CUDA API summary report on top 10 CUDA calls based on time usage. and we clearly see that like the 73% of runtime is spent on CUDA launch kernel, and this is the most expensive call by far. And this indicates that actually most time is spent on launching kernels. So this can be optimized by, for example, using less but larger launches, kernel launches by increasing batch size. Second screenshot shows the CUDA GPU kernel summary as the main contributors to the GPU compute time. For example, the codes here starting with NCHW, they correspond to 16% of GPU time. They correspond to the conversion between PyTorch and NVIDIA optimized tensors internally. And the next one is this batch norm is expansive in forward and backward passes. They take about 17% of the GPU time, and other ones can be weight or data gradient operations. So those can be optimized by using low-level GPU programming or using GPU external libraries or using mixed precision. So for the multi-GPU case, PyTorch DDP is very efficient. So it is a distributed data parallel library. And the idea is each GPU receives a unique subset of the input batch and process these subsets independently. So all share and average the updates so that the model stays synchronized across devices. And PyTorch handles this in the background. So this is the profiling output from multi-GPU case, and this is the top 2 activity from the command line profiler. It shows that it is the communication is dominant here. For example, all reduce is for synchronizing the gradients, and broadcast is to broadcast the model weights. So this is like 53% of GPU kernel is spent on these collective operations. And when we look at more in detail, for example, you can visualize this raw profiling outputs with the Insight Systems GUI. And here we zoomed in the timeline per epoch activity per GPU. And we noticed that one of the GPUs is computing while others look like waiting. So this looks like a load imbalance. So for example, one GPU gets a larger or a slower batch compared to others. So this can be one thing to focus for optimization. So as a result, performance engineering of this application, this workflow, continues with repeating these processes of profiling to identify bottlenecks and then optimizing to address the bottlenecks until you are happy with the performance. So here's a quick speed up analysis on the training time with respect to the number of GPUs using different hyperparameter values. And the fastest one is at the bottom, for example, at 4 GPUs, here this one with dark blue. At 4 GPUs, for example, the training time took about 6 minutes. And then the speed up from 1 GPU to 4 GPUs is about 2 times speed up. So it means 4 GPU doubles the performance compared to single GPU. And this shows a moderate parallel efficiency. So, okay, so as we talk about workflows, systems, and performance, it is easy to forget that the real driver to success is people. And modern research and computing now demands interdisciplinary collaboration. bringing together domain scientists, AI researchers, HPC specialists, performance engineers, and software developers. And no single person can know it all anymore. That means we need teams with diverse skills and backgrounds. In particular, the number of women in HPC is still far from where it needs to be. And Women in HPC organization aims to promote a diverse and inclusive HPC workforce to increase the participation of women and other underrepresented groups. And chapters and affiliates fulfill the mission of Women in HPC locally by organizing their own events, workshops, and managing volunteers, like yours in Women in Geospatial Ireland chapter. I am on the committee of Women in HPC Ireland chapter, and we were formed in late 2024. It is a cross-border collaboration funded by Zara Birch from NIHPC at Queen's University, and Katie O'Connor from ICHEC at University of Galway, and Tanya Malik from HPC Nexus Lab at TU Dublin. Thank you very much, and thanks again for the invitation and for opportunity to present about ICHEC HPC and women in HPC. And I'm happy to answer if there's any question or if you want to reach out later. So this is my contact email, and we are www.ichec.ie. Thank you very much.
Thank you. That was very interesting. It was a great insight into performance engineering. If anyone has any questions, they can put it in the chat. I have one or two questions myself. The Casper you mentioned, it's going to be somewhere in Ireland. Any idea of the location?
It is not officially announced yet, so we are not sure.
And
Yeah.
has thought, just with in light of what's going on in the news, into how it's going to be powered in terms of renewable energy, or will it be relying on the grid, or how does it compare to, we say, the data centers?
Yes, definitely. This is a big consideration. Cooling is very important. There are more energy efficient coolings now for modern HPC and data centers rather than air cooling systems. So again, we don't know. It is not. I mean, it is in progress now. The meetings, and so nothing is certain. But definitely it will be on energy consideration, will be a priority.
Sounds good.
Mhm.
Do we have any
While
questions?
people are typing, maybe I can you hear me? I'm good. I have one question there.
Yes.
So a very interesting thing Sandra raised there regarding energy, but I will ask different questions. Sorry. You know, for us in EU and GIS, we're predominantly like dealing with Python, and we have this kind of like Python is slow. It's okay. Like it's right now we have most of the libraries in Python. So do you have any ideas and people starting to learn about optimizing using Python for, especially for like EU and GIS people?
Yeah, Python is dominant in building these AI workflows, definitely. In HPC, there are like tools for workflow orchestration, like Apache Airflow, for example, or for example, for resource management, Slurm handles the resource management. But as a user, you don't need to concern with learning these tools rather than deploying your workflow. So you don't need to learn about the techniques of Apache Airflow, for example, or Slurm, you know, but definitely Python is required. And programming, for programming the ecosystem, Python ecosystem, I think where you develop your codes, is it PyCharm or let's say VS Code, or which environment you use to develop your codes is again up to maybe your preference. for example, CI/CD is very important. If you are working in a team, you share your code, everybody collaborate, and you see the contribution of everybody in the team. So CI/CD is very important now. And what else? Yeah, if we go one step back, linear algebra, probability, statistics, and maths, for example, derivative integration is important to understand these the maths behind not everything in detail, but how it works a little bit behind the scenes. So a little bit of maths background, Python programming skills, and ecosystem where you develop your codes, and libraries as well. Pandas for maybe for data, handling data, NumPy, for example, for maths calculation, or scikit-learn. But if you want to run on GPUs, there are libraries like CuPy, for example, like NumPy on CPU, correspondence is CuPy on the GPU, or PyTorch or TensorFlow.
All right. Yeah, thank you so much. Thank you so much. A lot of pointers to go. Yeah.
Thank you.
I just have another question myself. Could you just explain a bit more about AI Factory? You touched about it in your presentation.
Yeah, so these are like AI optimized supercomputers in Europe. There are I forgot, but I think 7 or if I have it in my presentation, a number of HPC centers in Europe, and ICHEC will be like a bridge between local users, Irish researchers, with these infrastructures. So there will be like a project applications, and all these will be announced soon. So it is now the project is live, and hopefully we will be starting to announce further details about how you can access the project application soon from our website and also LinkedIn pages. So these computers are all like equipped with all these AI tools, workflow tools, orchestrations. And as a computational scientist in ICHEC, we will be helping users to use these machines by trainings. We also have a help desk, for example, for any short, immediate queries. So, yeah.
That's very exciting.
Yeah, exactly. We are also very excited about it.
Okay, I don't see any questions coming through. So I'm just going to thank everyone for joining us today. And a huge thank you to you, Buket, for sharing your time, your insights, and your experience with us. We want to thank all our attendees for being part of our sessions. Their engagement and continued support of our webinar series is great. Before we sign off, just a quick reminder that today's recording will be available on our YouTube channel, so feel free to rewatch it or share it with colleagues. I want to say thank you and enjoy your day.
Thank you very much.
Thank you so much. Thank you.